Is it live and recording?
I still need to record to YouTube. Give me a sec.
Okay, yeah, it says it's live on YouTube.
Yeah, it's like buffering right now, but it should be ready. And oh, yeah, it's live now. All right.
Live, okay, cool, thanks. Yeah, hello everyone. Welcome to the session 7C of STOC 2020 on optimization and learning. Our technical host for this session is Jean Lee. Thank you, Jean. Let me remind everyone of the format briefly. Each slot is 10 minutes, 5 minutes for the presentation and 5 minutes for the questions. The audience can ask questions either through the Q&A feature or through the raise your hand feature. I will read out the questions asked through Q&A at the end of the presentation. And if someone raises their hand, we will unmute them and they can ask their question. You can also ask your questions on the Slack channel for each paper. After this session has ended, if people want to hang out with the speakers, they can use the raise your hand feature and we can then promote them to panelists and you can maybe hang out for around 20 minutes or so. Okay, so let's start. So Jonathan, maybe you can share your screen.
Yeah, let's do that.
Okay.
Okay.
Okay, so yeah, so our first speaker is Jonathan Leek, and he will tell us about computability of maximum entropy distributions in the continuous domain. Okay.
Yeah, thanks for that introduction, and thanks for having me. Yeah, so I'm going to talk about continuous max entropy distributions. This is joint work with Nishith Vishnoi. Okay, so the first thing I'm going to discuss is the setup. So this picture is supposed to give you a picture of what's going on. So the idea is you have some M, which is often a manifold, but it could be a discrete set. You have some measure supported on M. And then you look at the so this is embedded in R to the D, and you look at the convex hull of this, and that's cut out by this gray down here. And you pick some A in that convex hull, and the thing we want to find is the distribution on M, which has expectation A, which minimizes scale divergence with respect to this base measure that you started with. And the reason why we call this a max entropy distribution is one of the specific cases that has been studied before on this is when M is a discrete set and mu is the uniform distribution, and then this is exactly the distribution which maximizes entropy. So in the continuous case, these distributions have kind of arise in connection to a number of things, sometimes implicit, sometimes explicit. In particular, I'll point out the interior point methods thing here is the entropic barrier function is very related to the dual of this convex program. And the barrier-centric quantum entropy we'll discuss on the next slide. But before we kind of get into this, I'm just going to raise like sort of right off the bat issues that come about from this picture. And the first one is you can't really explicitly describe M. You can't list all the points if it's a manifold, or even if it's discrete and exponentially sized. But even worse, this optimization is overall functions nu on this manifold potentially, and so that the search space could be infinite dimensional. So these are right off the bat issues we have to deal with to get even an algorithm. But the nice thing is, if we go to the dual program, we immediately get something that's actually finite dimensional. And because we have strong duality in this case, we actually know an explicit form for the max entropy distribution, and we can just solve this dual program. In particular, if we find the optimal y, which is denoted by this y star, then we have the density. So that's nice. So then the questions become a little bit different. They become, okay, can we find this optimal dual solution efficiently? Can we sample from the corresponding distribution efficiently? Okay, and we're going to restrict to the dual from now on, since this is going to be the main thing we attack. And one particular example to keep in mind throughout is, let's say our M is the set of all Hermitian PSD rank 1 projection matrices. The convex hull of this is the density matrices, PSD trace 1. And there's a natural unitarily invariant distribution on the rank 1 projections. And if we pick A, something in the interior, I kind of say that up in the strong duality, but we'll always assume interior A's. That's just going to be something invertible. And it turns out with this setup, this minimal KI divergence is exactly how the barycentric quantum entropy is defined. It's some continuous distribution on all pure states related to this density matrix, which if you compare to the von Neumann entropy, is a discrete distribution on the pure states corresponding to the eigenvectors. So this is somehow some continuous generalization in a certain sense. Okay, so let's then look at the main results. So we have this setup. We have some A sufficiently in the relative interior with the M and its mu. The first theorem is then something general. So we can approximate this Y star, okay, given that we have two things. So we need this mu to be balanced, which means something like it's spread out. We'll talk about that later. And the sort of more difficult thing to get is access to this strong counting oracle, which is just, you know, the ability to efficiently evaluate the dual objective and also its gradient, right? And this is integrating over some manifold potentially. So this is non-trivial. But the thing is, in particular, in the case of rank K PSG projections, we do have this strong counting oracle, and we'll talk about exactly how we might get that later. And that also for the case of K equals 1, which is this barycentric quantum entropy, we have that as well, and we also have the ability to sample in that case. So as a corollary, we get this approximation algorithm for the quantum entropy, and we can also sample from the corresponding distribution. The last result I'm going to put on this slide is something a little bit off from the rest of this. It is sort of more of an observation rather than maybe some thing where we had to really prove something over the course of a lot of work. It's that the Gomans-Williamson STB rounding method from their max cut paper actually can be considered as drawing from a max entropy distribution. So this is just another example of how these things maybe have come up implicitly in other places before. This is just maybe an interesting fact that came out of this. Okay. So the algorithm, right, once we go to the dual program, we basically just need to optimize, and it's a convex function that we're optimizing, so we just use the ellipsoid algorithm. To use that, we need a couple things. The first thing is we need some starting bounding box where we're guaranteed some optimum is, and basically the balance property gives that to us. I won't talk about how. I'm just going to talk about what balance means here, and essentially means that I said sort of spread out evenly, sort of somewhat like uniform. It's not very small anywhere. And this is supposed to emulate the discrete uniform measure case. And most nice measures that you could look at have this property. But the second thing is a little more interesting, or a little harder maybe, and it's this counting oracle. In the case of rank 1 projections, basically you can transfer to the simplex, which is pretty interesting. This is also what allows sampling, because we can sample from the simplex and bring it back. In the rank K, we need something a little more high-powered, which is this HCIZ formula, which is just interesting in and of itself because it allows us to give an integral over some group as some determinant. And the third thing we need is some other balance, but that's not very hard. And so that's kind of the main result and sort of how the proof goes. And so future directions, basically we can consider the rank K projections case as taking some diagonal matrix, conjugating by the action of unitary group, and looking at the orbit that's cut out, and doing this whole kind of framework on that. But we could have changed that diagonal matrix to any other real diagonal matrix. And we could have even changed the group that's acting on it and look at these different orbits. Can we do similar things there? And also in terms of sampling, we were able to get sampling in the rank 1 case by transferring to the simplex. There's something similar you can do in the rank K case, but it's not really clear how to do everything. Things are more complicated. So that's an open problem. But even more generally, can you go beyond that? Can you go to other groups, these other orbits? Can you do these things in more general cases? And that's it.
Thank you, Jonathan. Questions? Okay, so I have a question. So in the longer version of your talk, you said that you can compute the entropic barrier for polytopes using this?
Yeah, so there are a couple caveats to that. So this sufficiently in the interior thing, it becomes much more of a thing there because now if you're too close to the boundary, there's some dependence on 1 over the distance to the boundary rather than log of that. So you're going to have to kind of deal with that. And we also in the paper don't exactly spell out the details. There are some extra things that you have to make sure that you can do when you're computing these integrals over polytopes. And it appears that you should be able to do that. I've sort of written some stuff down, not in the paper, and I feel pretty good about the things that need to be done there, but it's not explicitly written down.
So yeah, I guess to run an interior point method, you need to like differentiate the entropic barrier and run Newton steps on it. Like, can you do that also?
Um, so you should be able to differentiate, like get the gradient. I mean, is
The
this?
gradient and the Hessian, right, right.
Yeah. So definitely, I think the gradient. The Hessian, I'm not as sure of, but I think that this method, at least I see, to run the actual interior. Okay, so
Right, right,
basically, I'm only talking about like actually evaluating the entropic
right, right,
barrier. In
right,
terms of actually doing interior point methods, I guess I haven't
right.
looked as much into that. But I imagine if the gradient is doable, probably the Hessian is not so hard, I would guess.
I see. Okay, thank you. Okay, still don't see. Yeah, actually another question. So you, yeah, I guess in the rank K projection setting, you said that you can compute the dual optimal solution, but cannot sample from the distribution, or
Yeah.
don't know how to do it yet.
Well, there's. Oh, sorry. Keep going.
So yeah, my question was that what are some other uses that, so yeah, why would one want to compute the dual optimal solution? Like what would one be able to do with that?
Yeah. So I mean, probably at the end of the day, sampling would be more the active thing you would want to be able to do. And so maybe it should be thought of as there are some candidates, and Nishith and I are actually thinking about how to go about sampling in the rank K case. And more generally, it's just that it was a little bit surprising to me maybe that kind of computing the dual optimum, I kind of expected, because I think in the discrete case, it's equivalent sort of to being able to sample. And it seems like in this case, that's not really the case. It seems harder to sample even once you have that Y star. So maybe you could maybe think of it as doing this optimization problem is sort of the first step you would need to be able to do in order to get to sampling. And like I said, in the rank 1 case, sampling sort of works by going to the simplex and coming back. And there should be something similar in the rank K case, but it's just much more complicated.
Okay, thank you.
Yeah.
Okay, thank you, Jonathan.
Yeah.
So yeah, maybe you can unshare your screen. Yeah, Houghton, you can share your screen.
Okay, let me do that now. Okay, can you see the screen?
Yes, I can see, yeah.
Okay, great.
Okay, okay, yeah, so let's start. So yeah, our next talk is by Houghton Jian, and he will tell us about improvements in cutting plane methods.
Okay, thank you for the introduction. So this talk is about an improved cutting plane method for convex optimization, convex concave games, and its applications. This is joint work with Intatelli from UW, Zhao Song from IAS in Princeton, and Sam Wang from MSR. So the problem we studied today is the following feasibility problem. We're given a convex set K that is in Rn that is contained in a box of radius R, like in the picture. Our goal is to either compute a point in K or prove that K does not contain a ball of radius epsilon. So the information of K given to us is through a separation oracle. When queried with a point X in K, as in the picture, the oracle outputs yes. In this case, we're also done because we already found a point in K. If X does not lie in K, then the oracle outputs a hyperplane that separates X from K. It also tells us on which side of this hyperplane K resides, so we can chop off the other side of the hyperplane and shrink our search space. That's why these methods are called cutting plane methods. And so in fact, this feasibility problem is general. It also encapsulates convex optimization problem. So there's a long history of cutting plane methods. In the interest of time, I'm only going to focus on two of them. These are state-of-the-art results in one way or the other. The first one is by Vaidya in 1989, and the second one is by Lee Sidford Wang in 2015. So both of these algorithms achieve an oracle complexity of n log kappa, where kappa is nr over epsilon. To just recall, n is the dimension of a problem, r is the radius of the initial box that contains the convex set K, and epsilon is the accuracy parameter. So just recall that we either want to compute a point in K or prove that K does not have a ball of radius epsilon. That's the epsilon here. So both these algorithms have oracle complexity, makes n log kappa calls to the separation oracle, and one can show this oracle complexity is tight. So let's only focus on the running time part. So in particular, Vidia's algorithm has a runtime of n to the omega plus 1 log kappa, and Leek for 1 has a runtime of n cubed log kappa cubed. So when kappa is exponential in n, then the Vidia's algorithm is better. This corresponds in particular to continuous settings such as computing market equilibrium, etc., where you really need to take the error parameter of epsilon to be exponentially small. On the other hand, if k is equal to polynomial in n, then Leek for 1's method is more preferable. So using their method, they got improved runtime for a few well-known combinatorial optimization problems, such as submodular function minimization. So given these results, one natural question one might ask is, can we achieve the best of both worlds? Can we get an algorithm that works, that is good for both when k is exponential and when k is polynomial? And in this paper, we give an affirmative answer to this question using the volumetric center method of Vidia together with a lever score maintenance data structure. So in particular, our algorithm achieves the optimal oracle complexity of n log kappa, and the extra runtime is n cubed log kappa. So essentially, what we show is that our algorithm runs in n squared time per iteration on average. And moreover, we believe this n squared time cannot be improved. I'd like to remark that there's no extra log in this n squared time per iteration. So let me spend maybe 1 minute to briefly talk about what this lever score maintenance is. This is our key techniques. The bottleneck of the previous algorithm by Vidia is to maintain certain lever scores. So what are these lever scores? I'm not going to give a formula for them, but geometrically, if you think about the polytope we maintain using the separating hyperplanes, so this polytope contains our target set K. So if this polytope is sufficiently rounded or isotropic, although that's not the precise use of words, then sigma I, these lever scores, roughly measure how far constraint I is from the center of this polytope. So it roughly measures how important each constraint is. So how do we maintain these sigma i's? So in our paper, we write delta sigma I, which is the change in lever score, as an integration that involves a certain projection matrix. And there's some recent work on projection maintenance for linear programming by Cohen-Lee Song and by Wanda Brandt. We can use these to approximate our projection matrix, but this alone is not enough to imply the result. We also need to do various other numerical tools, such as interpolation of the integration, fast matrix multiplication, sketching, to speed up the computation and control the error. Not going to go into details on these, but roughly here's this is how our data structure looks like, and refer to the full version of this talk for details on this graph. So I'd like to finally talk about a few generalizations and applications of our new cutting plane method. So the first one is a conditional one. So if some matrix multiplicationer be able to do an n by n to the 2/3 matrix times an n to the 2/3 by n matrix in time that is close to n squared, then we can make our cutting plane method deterministic. So so just one side remark, our cutting plane method is not deterministic because we need to do the sketching. But if one can do matrix multiplication faster, as shown here, then we can make it deterministic. And in order for wider applications, we also extend our result to the more general convex concave setting, where you want to compute and approximate saddle point. And using this convex concave extension, we're able to obtain improved runtime for several problems in market equilibrium computation. This includes linear exchange market, Fisher market, etc. So that's basically everything I want to talk about. I'd be happy to take questions. Thank you.
Thank you, Hayutin. Yeah, so we have a question.
Yeah.
Nice talk. You say that you believe the runtime of your algorithm is optimal. What makes you believe this?
Okay, yeah, this is a good question. So yeah, I think the major reason is that in cutting plane method, so you have a polytope, and you don't know what extra constraints you will get later on. And in order to compute the information for that, you need to take n squared time to roughly approximate the leverage score for those newly arrived constraint. I think that's probably the major bottleneck for this n squared. Oh, there's also, by the way, there's also some evidence from this literature on dynamic algorithms lower bound. Although those are not directly related, but they were able to prove something that n to the 2 minus epsilon is not possible for certain dynamic problems in certain models. But again, those models are different from the models we are using here.
Okay, so we have another question by Chandra Chekuri. Is the algorithm Las Vegas randomized or Monte Carlo?
So our algorithm is I think basically we use this JL, Johnson-Lin dense-Strauss. So I think it's like with certain probability we succeed. Otherwise, like with very, very small probability, our error blows up. I think that's the answer to that.
Right. Okay. So yeah, I also had a question. So your algorithms use fast rectangular matrix multiplication, right?
Yes.
So can you say a bit about how do you think these algorithms will perform in practice?
So honestly, I feel because our data structure, our way of approximating this integration is still kind of complicated because we need to incorporate a whole bunch of different numerical tools. So I wouldn't say this is a very practical algorithm. It's just like a theoretical thing.
Right. Yeah. Okay. Thank you.
Yeah, I believe most of these recent data structures are like kind of also complicated in this sense. They're only, I think the results there are only like theoretically interesting.
Okay. Thank you. Okay. Thank you, Houghton.
Okay, thank you. Let me stop sharing.
Yeah. So Vitaly, you can share a screen.
Mute myself. Share screen. Desktop. Share.
Yeah.
Play from start. Are we good?
Yeah, looks good. Okay, so our next speaker is Vitaly Feldman, and he will tell us why memorization might be required for generalization.
Thank you, Ankit. So the goal of this work is to explain why the deep learning algorithms eagerly memorize training data labels, even when the training data includes a significant fraction of mislabeled examples and outliers. And most of you have probably heard about this, but for those who didn't, there is plenty of well-known evidence. For example, when trained on common image and text classification data sets, deep learning algorithms fit the training data very well and typically have an error on the training set, which is very close to 0. And at the same time, the test error is significantly higher. So the learning problem is not an easy one. We also know that these data sets include a non-trivial fraction of outliers and mislabeled examples. And the only way to fit the labels of points that the learning algorithm cannot classify correctly is to effectively memorize those labels. And there are also more extreme experiments showing that deep learning algorithms eagerly memorize even random labels. To make this more precise, I define label memorization as follows. For dataset S, which contains n examples, an index of one example in the dataset, and a learning algorithm A, the memorization value for that example, ith example is measured as the difference between two probabilities. The first one is the probability that the algorithm fits the label of the ith example. And the second one is the probability that the algorithm fits the label of the ith example when that example is removed from the data set. The goal of this definition is to capture the intuition that fitting an example that an algorithm cannot classify without seeing it requires memorization. So as I mentioned, label memorization is very common in practice, and it has attracted a lot of interest in the past couple of years. However, it is not explained by existing work. In fact, it appears to contradict the way we tend to think about learning and the way learning is often taught in in our machine learning courses. Learning is supposed to be about finding patterns and not fitting individual labels, and memorization is supposed to lead to overfitting. So that's the question. And at a high level, my explanation is based on an observation that natural data distribution are not homogeneous, and they are better thought of as consisting of numerous subpopulations or clusters, which are quite different from each other. And here is an example from this CFAR 10 dataset class of birds. And as you can see, these images consist of hundreds of different species of birds taken from different angles, at different magnifications, different backgrounds. So these subpopulations are quite different from each other, and an algorithm may be unable to predict on a subpopulation well without observing any representative from that subpopulation. And we'll be particularly interested in looking at subpopulations whose frequency in the true distribution is on the order of 1/n. From these subpopulations, we'll, in most cases, observe only a single example. So that example would need to be memorized because it's different from many other examples. And another interesting effect that happens is that we will also, for subpopulations which occur, which are very infrequent, very rare, basically outlier subpopulations, we'll also observe just a single example. So based on just the count of the number of examples in the populations, well, it is impossible to tell subpopulations which occur on the order of 1/n and are useful for generalization, and those which are very rare and are effectively useless. And also, when you only have a single representative from some distinct subpopulation, it may be impossible for the algorithm to distinguish a correct label from a noisy one, because again, the algorithm cannot predict it very well. Again, these infrequent examples require memorization and may be hard to distinguish from the outlier. But the questions are, these sort of infrequent subpopulations on the order of 1/n, are they important for generalization or not? And the answer depends on the distribution of frequencies. And what we know about this distribution is sort of colloquially that natural distribution are usually long tail. And there are some measurements done by practitioners which show that these distributions of frequency tend to follow the classical power law distribution, and most often zip law. And for these distributions, we know that the frequencies on the order of 1/n, which are sort of important, can make up a significant fraction of the whole distribution. So that's the high level. These are important frequencies. They require memorization, also cause memorization of other things. Let me mention, roughly explain how I turn this intuition into a model that captures this intuition. The key element of the model is that in this model, the distribution over the domain is defined to be a mixture distribution of some subpopulation. And the frequencies in this mixture, which are just these mixture coefficients, are assumed to be chosen randomly from a prior distribution over frequency, which is denoted by pi. And the goal of the learning algorithm is to minimize the expected generalization error of a learning algorithm, where expectation is also taking over the choice of this distribution over the domain, because there's a random choice of these mixture coefficients. So for this class of models, I show that fitting all examples that are unique representatives of their subpopulation is necessary for achieving close to optimal generalization. And this result is quantitative, and it shows that the cost of not fitting is characterized by the prior distribution over the frequency, and specifically by the total weight of the frequency on the order of 1/n. So the conclusion of this result is that if the data distribution is long tail, then the cost of not fitting is high, and otherwise there is no cost to not fitting. And finally, this result is related to memorization using this simple definition that I described. So to conclude, this work shows that label memorization is necessary for achieving close to optimal generalization whenever the data distribution is long tail, and many natural distributions are long tail. And the reason why memorization is so common in practice is that algorithms that we use are implicitly tuned to to basically work as well as possible on long tail distribution. And let me also mention that this result is not specific to deep learning and suggests that memorization is an inherent part of learning more generally. Another thing that I would like to mention is a very recent question Zhang, in which we empirically validate the ideas in the theory that I have just described on several image classification data sets. Specifically, we find which training examples are memorized and how memorization affects the accuracy on the long tail of the data distribution. And you can find the paper on my website. That's all that I have to say. Thank you, and I'll be happy to take questions.
Thank you, Vitaly. Questions? Yeah, so I was wondering whether your work also shed some light on how algorithms should go about memorization. Like, I guess in your longer version of talk, you said that memorization of some examples can be good for generalization and memorizing some examples can be bad for generalization. So how do the algorithms make that distinction?
So maybe that's a good question. To some degree, the point of the work is, in many cases, it might be impossible to tell between these two scenarios. So memorization of good examples is useful, but because these good examples, which are rare, we know very little about them, or learning algorithms knows little about it. It may not be able to distinguish them from the bad ones or useful or useless ones, at least. So in some sense, there is basically the answer is that it may be impossible to tell between those two in many scenarios, and as a result, that's why we sort of see this memorization of useless examples in practice.
Okay, thank you. So we have another question by Jerry Lee. Does the bound apply to other long-tailed distributions?
The bound is in terms of, in general, for any distribution. The bound is formulated in terms of the prior and the number of examples that you have. So you can plug any prior you like, and but the cost of not fitting will depend on that prior. So if the prior is not long-tailed, it may not be necessary to memorize to achieve the close to optimal performance.
Thank you. Another question by Sasha Nikolov. Is it important that the mixture weights are sampled IID from a prior, or are the results robust to other setups?
So I think some level of independent. So one can probably. So for my in my paper, it's I really use that IID assumption of IID up to normalization. But I believe that other ways to define, for example, by randomly permuting those weights, sort of sampling without replacement would work. Probably other things, it should be relatively robust, but sort of actually giving the bounds for these non-IID settings might be much harder, basically.
Thank you. Okay, so maybe I will take one more question. Does the theory also give some reason why the test error is non-trivial as opposed to what a random label would give? From what I understood, the theorem says memorization is necessary, but not necessarily sufficient.
I don't, sorry,
yeah.
Can you read it again? I don't.
Yes, does the theory also give some reason why the test error is non-trivial as opposed to what a random label would give?
Okay, the theory maybe okay, maybe it's my interpretation of what the question might be saying. So yes, the theory does explain why the test error is high, and the reason is that in these long tail distribution, there's always remains a fraction distribution that you haven't observed at all. So that's the part of the distribution which is important for achieving high accuracy, but because you haven't observed it, you won't be able to predict, achieve any accuracy there. So That's why the test error, the test error is going to be necessarily high. You haven't, unless you have a really huge amount of data, you won't be able to achieve perfect accuracy.
Okay, thank you. Thank you, Vitaly.
Okay, thank you. I guess I need to mute myself and screen share.
Yes.
Okay, stop share.
Okay, yes, Sitan. Maybe you can share your screen. Okay, yeah, I can see it.
Great.
Okay, yeah, our next speaker is Sitan Chen, and he will tell us about learning distributions from untrusted batches.
Great, thanks for the introduction. So this is joint work with Jerry Lee and Ankur Moitra. And broadly, this work falls under the agenda of designing learning algorithms that are robust to a constant fraction of errors. But the specific work I'll be talking about comes with sort of a crowdsourced learning twist. So this question of learning from untrusted batches was introduced by Chow and Valiant a couple years back. So let me define it. Let's imagine you're some centralized server trying to train, let's say, a spell check over mobile devices. And maybe one of your tasks is to understand what the distribution over misspellings of a given word is. So I want to learn some discrete distribution, P, which is over some finite domain of size n. Okay, how does the learner proceed? Let's say we draw user data. So every user device is going to send a draw from this underlying distribution to me, the learner. And my goal is to aggregate the user data and try to learn the distribution P. Okay, so as I've stated it so far, this is nothing more than vanilla discrete distribution learning. The simple question you can ask is, what if a constant fraction of the users conspire to give me adversarially chosen samples to skew my estimator? Okay, so a fundamental but not very interesting limit is that a priori it's impossible for you to distinguish whether your samples came from P or from some any other epsilon perturbation of P. Okay, but in these crowdsourced settings, one can imagine that what you get from the users isn't just a single draw per user device, but perhaps a batch of K draws. So let's now suppose that every user who is not corrupted gives me, in fact, K IID draws from the underlying distribution. The hope is that with this additional redundancy, that as you take K to be bigger and bigger, you can hope to drive this information theoretic limit in terms of optimal error to be smaller and smaller. Okay. This is sort of motivated by applications of federated learning, but I won't go into details about that. All right, so what is known about this learning problem? So the original work that introduced this problem showed a basic limit at roughly epsilon over root k. So they show information theoretically that this is impossible, regardless of how many samples you have, to get below epsilon over root k. And at a high level, this is just because this is the rate at which TV tensorizes, this root k factor. All right. In particular, in terms of algorithms, they also introduce algorithms that inherently run in time either exponential in the domain size or in the batch size, k. And the actual question you can ask is, can you achieve this limit of epsilon over root k efficiently? So in sample complexity at runtime, polynomial null parameters. Okay, so the first result of this work shows that the answer is essentially yes, up to a root log factor, and running in time and samples quasi-polynomial, we can actually achieve this learning goal. Okay, so now let me turn to the main result of this work, which is a bit of a different spin on this question. So in the case where we actually have additional prior information about the structure of P, can we hope to do better in terms of sample complexity? So let's imagine our P now is, if I arrange the domain elements from 1 to n, from left to right, and plot the probabilities that P assigns to those elements, maybe this distribution P is actually monotone, or maybe a mixture of log concave distributions. Can we hope to get better sample guarantees in this case? So concretely, let's imagine P is approximated by some piecewise polynomial, and define the parameter L to be this quantity here. Roughly speaking, this corresponds to some notion of VC complexity. And typically, for such applications, this L parameter is going to be either logarithmic in or even independent of the domain size. And so the main result of this work is to show that you can actually leverage this kind of prior structural information of P being approximated by a piecewise polynomial to get dramatic sample complexity savings. So instead of running in sort of quasi-polynomial with a dependence on n in the number of users, we only need to run in roughly L to the log 1 over epsilon users. Okay? And here L, again, is significantly sublinear in the domain size. Okay, so let me just say a few words about the techniques. So as with all the existing works on robust statistics, the basic idea is to search for a large subset of the data that satisfies certain sub-Gaussian moment bounds. But the key twist in our setting is that we need to do this not in every direction, but only in directions with a bounded number of sign changes. The point is that the number of such vectors is a very small fraction of the Boolean hypercube, which is what we need in order to get our sample complexity savings. Okay, but how do you search for how do you even quantify over this set of test vectors in sort of an SOS fashion? Okay, and here's an example of a bounded sign change vector. The key idea is that vectors which are sparse in the number of sign changes are also sparse in the so-called Haar wavelet basis. So if we look at an appropriate notion of analytic sparsity in this basis, we can actually use sum of squares to achieve this search problem. Okay, so let me just conclude. The key takeaway roughly is that you can use these method moments techniques like sum of squares to actually exploit this kind of prior structural information about the distribution to get dramatic sample complexity savings. Let me also mention some concurrent and follow-up work. So independent of this work, Jane Orlitsky showed actually a polytime algorithm for the unstructured case using a non-SOS algorithm. And then subsequent independent work by us and by the same group of researchers showed that in the structured case, you can actually achieve similar polytime guarantees by combining the Haar sparsity framework of this work with the polytime algorithm from Jane Orlitsky 19. And the main point is that actually the algorithms we end up getting are actually implementable, so I encourage you to check out our recent preprint on arXiv for some discussion of that. Okay, that's all. Thanks.
Thank you, Sitan. Questions? Okay. So yeah, can you discuss a bit on when can you expect to speed up SOS algorithms in this robust statistics area using to make them actually implementable? When can you actually speed them up? Like, I guess for this problem you said that speed them up.
Yeah, great question. So at a high level, like the idea is that okay, so what is this polytime algorithm? It's sort of the other by now like kind of standard recipe for designing robust distribution learning algorithms. So this is the so-called filtering framework. So the basic idea is at every step, we're going to maintain a collection of weights, similar to sort of the SOS program that we use. We assign weights to every point that correspond to indicators for whether we think this point is corrupted or uncorrupted. And instead of using SOS to solve for to find a pseudo distribution over like weight assignments, what we do is we update the weights by searching for sort of a direction. So if you look at these test vectors, the set of test vectors, which have bounded sign changes, we want to look for such a bounded sign change direction for which the sort of data is like most skewed. And the point is that if we take the outliers in that skewed direction and sort of downweight them, the point is that whenever you do this downweighting, you're going to throw out more bad mass than good mass. So eventually, after doing enough of these filtering steps, you're going to end up with mostly good samples, and then you can just take the empirical mean. So usually the idea is, you have some notion of wanting to search for moment-bounded subsets, and ultimately you want to kind of integrate it into this filtering approach.
I see. Okay. Thank you.
Yeah.
Any more questions? Okay. Yeah. So thank you, Sitan.
Thanks.
So thanks to all the speakers for the wonderful talks and also the pre-recorded videos. So this completes the session. If the participants want to stay behind and hang out with the speakers, you can raise your hands and we'll promote you to panelists.